Okay, so thank you very much, Professor Bastia, for your kind and very long introduction. So I'm thankful to you. And first of all, let me thank Professor Samaris Jana and all the organizers for giving me the opportunity to speak here. This is really interesting forum during this pandemic that now we are connecting each other from every corner of the world, and then we are sharing our research. This is really becoming effective, very much effective. So thank you very much for this, and of course I'm grateful to you for giving me the opportunity to share some of my research currently that we are involved in last few years in ISAR Bhopal. So today I decided to speak on this topic because when someone has asked me for the title, initially I gave a different title and decided to talk about something else. But again, a few days back, I talked on that title in SES talk, so I changed it and I requested him to change. So thank you very much for permitting this also. Anyway, so today, in my talk, there are a few things that we will be covering here. A little bit about this, what is this hydrogen economy and switchable catalysis. So these are kind of keywords for my talk, and then liquid organic hydrogen carriers. Of course, from the name itself, I mean the English name itself, one can realize what are these, but slowly we will explain these things. So, in my group, I joined in 2011 in ISAR Bhopal, and then, we have been working for last few years on several topics. 2-3 leading research areas that we have been pursuing. Today, one of the leading research areas that we are really, involved very much, that we will be speaking today, is on this one. This is energy and alternative fuel. So how do we tackle these things, or how do we rather do our academic research on this area? We'll come to that later. Other than that, our group mainly is an organometallic group. So we do organometallic chemistry. We synthesize a lot of metal complexes, as is here in the center, MLN. And specifically, we are exploring nowadays metal NHC complexes. And then the target of this metal NHC complex design to act as a catalyst for several small molecule functionalization, as you can see here. One is carbon dioxide, another is alkane or arenes here, or H2 molecule or water molecule. So these are very very much respected in the domain of small molecule functionalization, because these are difficult to functionalize as such, so-called less reactive molecules or inactive molecules in some cases. Of course, in the morning, we have heard a very interesting talk on CH functionalization, CH activation and functionalization by Professor Maiti. So I'll not be talking about that today, although we do little bit on that area as well. So, today what I decided that on this energy and alternative fuel, what we normally focus in our group is on the liquid organic hydrogen carriers. Of course, there are many such, and then followed by that some CO2 conversion chemistry. But the whole idea is that we want to incorporate CO2 into the main energy cycle, basically recycling CO2 into the main energy or fuel cycle in a sustainable carbon neutral pathway. So that's the whole idea. It's a big big dream. Everybody, many researchers in the world, they are actually jumping in this field, and then they have been contributing for a very long time. Although, there are several problems and challenges today, it is there. And, so there are various ways to tackle those problems. One of them that we have been focusing, I will explain later. So why this particular area, or why this particular research is important, is very much understandable to all of us, because as we know that the CO2 emission, because of the fossil fuel consumptions in the atmosphere, now is really growing very high. So it's a controversial area whether it is contributing to the global warming or not. Some would agree, some would not, but that's not the point. The point is that the truth is that you have the CO2 concentration increased dramatically from the pre-industrial area to let's say currently or today. For example, this is accessed just a day before yesterday from the CO2 Earth website, which actually monitors the CO2 level by the observatory kept in Mauna Loa in Hawaii. So it is 413 ppm in the atmosphere. Last year during that same time it was 415 ppm. Last year it was 413 ppm. So you can follow here for last 1 year it is hovering around 414 to 416 ppm. So the point is that the pre-industrial area it was around 200 ppm. So we have doubled the concentration, and you see the red line here. 400 beyond 400 is a kind of red line, and 500 is a kind of warning regarding the temperature increase with respect to this global CO2 concentration in the atmosphere. So during all these things, then this international panel for climate change, that is IPCC, they keep on reviewing all these aspects of CO2 increase in the atmosphere. And so what they have suggested in the recent report is the latest report. It was published in October 2018. So they suggested that the global net human caused emissions of CO2 would need to fall by about 45% from 2010 levels by 2030. So basically we have 20 years from 10 to 30, and we have to reduce by around 45%, and then we have to bring it to net zero at around 2050. So the bottom line of this suggestion is that we have to keep the emissions, the remaining emissions would need to be balanced by removing the CO2 from air, and as well as we cannot emit too much again. I mean that you have to balance it in that regard, right? So then why it is happening? Because of the carbon enriched or carbon rich fuel that we are burning and emitting the CO2 to the atmosphere. But this is a problem recognized long back. I mean that time Professor Botris, he proposed a very interesting proposal that is called hydrogen economy proposal. As you can see, what he is proposing, that why fossil fuel, why carbon-rich fuel? Rather, you use hydrogen gas. So if you use hydrogen gas as a fuel, your byproduct is water. And then from water, you do the electrolysis here and then bring the H2 back into the chain, so that overall it's a carbon neutral process, and at the same time you are not emitting CO2. Of course, there are some issues here as well, but that's not more important here. The most important, although it is a very nice looking proposal, but it failed to be implemented broadly today in the society, although it is proposed in long back, and then after that lot of hydrogen research happened even today also. The thing is that hydrogen, here you can see the gravimetric energy density is very high, and here you have the fossil fuels. But the problem is that it is a gas, and then you have to store it somewhere. So you have to use it. If you have to use it, then you have to store it. Now the gas molecules to store, I mean, it's a real problem. I mean, it's not economically viable, rather it's technically also a problem. So basically you have to compress, you have to go to very low temperature, you have to pressurize it. So that is creating the problem of working with gaseous H2. So that's why this hydrogen economy with gaseous H2 more or less is not that much acceptable, although there are, let's say, hydrogen gas-based car nowadays. I mean, FCVs are there where people are creating 700 pressure, 700 bar pressure for giving you the H2, dispense the H2 into your fuel cell, and then it can work. It is there, but these are not free of problems as such. So if there is an alternative, that would be better, so that I don't have to handle the gas. So later on, realizing this problem, in 2006, Professor Ola and Surya Prakash, they proposed a very interesting system which is called methanol economy. What they are saying, that instead of hydrogen gas, you don't have to work with hydrogen gas, you work with methanol, which is also a fuel. You can actually burn methanol and you can emit CO2. And then what they're proposing, this CO2, again, you take the H2 from renewable energy source, you generate there, and then reduce or hydrogenate CO2 to methanol, and then you bring into the cycle again. So basically it is again a carbon neutral energy cycle. Every time you are emitting CO2, but you are also recycling CO2 by hydrogenation method. And methanol is a liquid, so you don't have to worry about the gas. Storage and transportation is perfectly fit to today's, let's say, fossil fuel transportation infrastructure that we have. So that's why this proposal has been accepted widely throughout the world. Even today, India is also proposing and working to use methanol. And probably you have heard that in aviation sector, and specifically in the military aviation, they have tested some 5 to 10% blend methanol into the jet fuel, and as well as in Nitin Gadkari, I mean, as per the advice from the Niti Aayog, they are now exploring into the ship transportation. So there also in India also, I mean, we are now working on methanol economy too much, and we are trying to substitute quite a bit percentage of methanol into the actual fuel. And based on this proposal, even, I mean, in practically in Iceland, there have been established one CO2 to methanol plant. So this plant is actually recycling CO2 and making methanol. This is in Iceland, and the hydrogen they are getting from a renewable energy source, and there it is a geothermal energy which is renewable, that is available there, and they are using that one. So it's practically implemented already. Other than that, what is the other option? Other option is that similar strategy, again proposed by Ola, you use formic acid. So same thing, you CO2, you hydrogenate with the renewable hydrogen to formic acid, which is also a liquid, and then formic acid can also be, dehydrogenated, get the hydrogen and then use in the fuel cell, and your emitted CO2 can be recycled again. So this is also similar carbon neutral energy cycle, and then you are actually recycling the CO2 with the help of renewable H2, and you are using the formic acid as a liquid fuel, which is much more easier to handle. So this proposal has also been tested in Netherlands. There is a group from school and college students led by Professor Pitko. What they have done, they have actually used formic acid as a fuel, and they demonstrated this to model cars. Okay, that they are working as as a kind of machinery which fueled by formic acid. So these are formic acid fuel cell model vehicles. But at the same time, they also overcome the problem of small model cars. Now they are running a city bus, fully equipped city bus with this kind of static generator of electricity from formic acid. And they are now working in a little bit larger scale at this moment, but they have demonstrated the city bus. And now they have, the team is called Team Fast. This is from Netherlands. And now they have opened a startup, Dance startup, and they are now working on this formic acid fuel in the whole transportation sector, and that is what they are now progressing very fast. So that means formic acid can also be used as a liquid, so you don't have to worry about the gas. Now, what are the other alternatives? There are other alternatives as well. So other than using CO2 based liquid fuels, you have aromatic based liquid fuels also. Look at this one. This is an aromatic compound. If you hydrogenate this, then you get a saturated aromatic compound. Now that means you have loaded hydrogen here, H2 molecule. It's a in our language it's a hydrogenation. Basically, you have hydrogenated these double bonds and loaded the H2 molecule here chemically. And then what you do a dehydrogenation here, get the H2 molecule, which is a fuel, and use as such whatever I described earlier, and whatever the discharge liquid that is coming from the dehydrogenation, again you recharge by H2, which can be produced from electricity, right? Of course, in all these schemes, your H2 is the key factor which you have to make from renewable to make all this viable. Like in Iceland factory, they are making it renewable H2 from geothermal energy. So that is very important here in all these schemes, that H2 is the key factor that we have to keep in mind. So this is very interesting, and this is some aromatic molecules, and not only that kind of, there are various kinds of aromatic molecules. For example, this is the pair, this is methyl cyclohexane, which is loaded one, which is storing the H2, and you do the dehydrogenation here, you get the unloaded and do the rehydrogenation again and do the cycle, and these both of them are liquid and can be used. So these have been proposed widely. Not only this one, you have naphthalene based, naphthalene decalene couple. This is more studied in industrial based, N-ethyl carbazole, and of course this has been tested also and demonstrated, this dibenzyl toluene, dibenzyl toluene, and then parhydrodibenzyl toluene for this kind of technology. But you look at here, the hydrogenation and dehydrogenation, if you look at the cycles, these are, PGM, that means platinum group metals. In all the processes are nowadays catalyzed by platinum group metal catalyst. So the problem of these things are the catalysis part. So you have to do it at a very high pressure and sometimes very high temperature also. If you look at here, 320 degrees centigrade, sometimes 20 bar, sometimes 30 bar. So but then above all, you have to also use platinum group metal. So this is the current state of the research in this field. But although it looks very much attractive, but then we have to develop good catalysts which are implementable in a more wider scale. Of course, we have to work much on this direction. So looking at this strategy of this liquid organic compounds like this, whatever I have shown, actually a Professor Wasser said in Germany, actually he demonstrated using dibenzyl toluene. He demonstrated this plant. This is also a plant which is utilizing this technology, this dehydrogenation and hydrogenation technology based on these liquid aromatic compounds. And then nowadays they are working to extrapolate this technology into the transportation sector. How? So you have the car, instead of your other tank, you have the LOHC tank here, liquid fuel tank here, which you can couple with the fuel cell that you have in the car, and using the H2, and then you can deload the discharged fuel and reload with the charged fuel. That is how. The advantage of these compounds you see here in these LOHCs, the gravimetric storage density and the volumetric storage density are very high compared to gas H2 or battery and so on and so forth. So this is the greatest advantage that you have, and most importantly, these are liquid compounds, so these are perfectly suitable with the current infrastructure that you have. So that means these liquid organic compounds are called liquid organic hydrogen carriers, or liquid LOHCs that we are calling by abbreviation LOHC. So this is the technology that we are talking about. So basically you have methanol, you have formic acid, you have cycloalkanes. Other than that also you can have different heterocycles to use in this technology. So main working chemistry here, you have to hydrogenate the hydrogen lean H0LOHC, and you have to dehydrogenate this H enriched or charged LOHC. So if you look at the current research with the N-heterocycles or N-heteroarenes or heterocycles, there are several current research is going on. It is initiated as back as 2009, but again, I mean, you look at here different heterocycles people are testing, and specifically people are testing to develop good catalysts. Here also some iridium-based catalyst you can see. There are also some iridium-based catalyst you can see. Here they are using 5 bar. They have reduced because it's an heterocycle. And it's a current research, of course. I mean, not only that, there are several other combinations of chemicals that you can use. All are liquids here, and it is listed here. This is N-ethyl carbazole and whole lot of heterocycles that you can have. Other than that, Professor Milstein and Surya Prakash from US, and of course there are some other groups also. They are using different types of liquid compounds, like amide-based liquid compound, which can be reversibly hydrogenated and dehydrogenated. That can also be proposed as a LOHC. So all these things are going on. But if you noticed all this research, then either the C double bond N or C double bond C chemistry, loading unloading, or the carbon dioxide chemistry, currently you need high pressure for charging, high temperature for discharging, and require different catalyst in these two states. So the charging, that means the hydrogenation, and the dehydrogenation, you need different catalysts. So things are a little more complicated and challenging as well, and that is what actually we have currently. So then why we came into the game and where we are. So our aim here is that what we thought at these cycles, that we need a very good hydrogenation catalyst, we need a very good dehydrogenation catalyst to work in this area. And by very good, I want to mean that I should work in very low pressure. I don't want to work with the high pressure system, number one. And as well as the discharging, I want to do at low temperatures. These are the major challenges that you have currently to work in low pressure. Probably, I mean, ideal would be the atmospheric pressure, so that you don't have to tackle the high pressure systems. And of course, the temperature below the fuel cell, that is 80 degrees centigrade, is much more desirable. And my system should be modular enough so that it can work with various LOHC platforms. So looking at these things and looking at these reversible systems, what we realize that we need a single bifunctional and switchable catalysis, so that if I have to work with single catalyst, then I have to switch back and forth, so that one state of the catalyst would work for the hydrogenation, and the another state of the catalyst would work with the dehydrogenation, so that I don't have to design different catalysts for different processes. Just my single catalyst would do the both the job. So that's the whole idea. But then how do we achieve? As we realized by this time that this is really a problematic area regarding the hydrogen activation. The main bottleneck is the hydrogen activation. You need hydrogen high pressure in all this research. So what we thought, so this is our hypothesis and thought at that time, that we wanted to have a single catalyst, but then of two different properties, but basically a dual character catalyst. So the one single character, another character, by the influence of some kind of stimulus. And we thought that the easiest stimulus would be acid and base, so that I can actually tune the property of the catalyst back and forth by applying acid and base. So then, what we thought that let's use a coordination based molecular switch, which has never been used in catalysis so far before our work. So we thought that if we change the coordination mode, look at here, this is a very interesting backbone. It's a imidazole or benzimidazole backbone, which has a protic NH here, that we can switch back and forth by the use of acid and base by this anionic motif and the neutral motif. So this is what we call it coordination switch. So this is an imino coordination, which is neutral, and this is an amido coordination, which is anionic. So that will control the electronics. In this case, the electron poor metal center will be the result. In this case, electron rich metal center will be the result, because this is a very strong sigma donor as well as pi donor, which is a simple, and this one is a simple Lewis acid donor. So this is what Lewis base donor, sorry. So this is what from the switchable perspective. But then I need a very good stable catalyst also. I should not decompose in these harsh hydrogenation, dehydrogenation conditions. For that we propose that we use NHC. This is abnormal NHC, pyridinium based abnormal NHC, which is also a strong donor. So that can give you sufficient stability of the metal complex, so that it will not degrade or it will not decomplex during all these processes. On top of that, you see here this basic motif you have still. So this lone pair is lone pair is the part of the aromatic system here, but still this lone pair is free, which can act as a base and can trap the proton. Whereas there you cannot do that. So that means I can have a proton trap in one state of the catalyst, and in the other I cannot have. Now all these things, all these parameters that I have discussed, all these elements, design elements, are extremely important in the research that I'm going to discuss now. Okay, so the whole idea is that the bifunctional hydrogen activation, how my switching the ligand platform will help, that is what I'm going to discuss. And then the electronic control, how I can use the hydricity, that means the hydride transfer capability, that will be controlled by the metal center. So with this design concept and hypothesis in mind, we started in our work, and then we designed our first coordination-based molecular switch based on an iridium system. You can look at, this is iridium Cp complex, and this is what the ligand that I'm talking about. You use a base, now you have an amido coordination, you use an acid, you have the imino coordination, so you can switch back and forth. Now, can we use in the hydrogenation? So for just to test the hypothesis, we took simple imine C double bond N bond, just to test whether I can hydrogenate easily or not. And delightedly, you see here, we just need 1 atmosphere hydrogen pressure here to hydrogenate or to load the H2 molecule into this imine C double bond N group. Interestingly, the imino state, as I explained earlier, as usual and as expected, it is an off catalyst. That means it is not acting as a catalyst for this reaction, whereas the amido compound, this is acting as a catalyst for this reaction. The reason behind this, as I told you, this bifunctional ligand moiety is acting to clip the H2 in a bifunctional manner, trapping the proton and going the hydride to the metal, whereas in this case, it is not possible. I will explain this in later, but then this is a kind of switchable hydrogenation. One catalyst is active, this one, another state, same catalyst basically, just I am using acid and base to switch this activity or inactivity. And that you can do actually in the solution in number of times just by adding acid and base. Of course, every time you are buffering, and fortunately in this case, this buffering effect has no dominant negative impact on this catalysis, we could run for a long time. But then that was for hydrogenation of the C double bond N bond. What about the dehydrogenation? For dehydrogenation also we screened a lot of catalysts, and then we tuned to a different metal here with a ruthenium catalyst, which has been found that this ruthenium catalyst in the inactive state for the hydrogenation actually became active for the dehydrogenation kind of reactions here, as I showed. So this is also a bi-state catalyst. You have two states switched by the acid and base, but then one state, as I explained earlier in case of iridium, one state regarding the hydrogenation reaction, this amido state is active, whereas the imino state, you just get no activity here. Now, after demonstrating the hydrogenation, what you do, you just change the state of the catalyst by using acid. Now this, this imino-based state is active in the dehydrogenation reaction, and the amido is off. So basically, it's a single bi-step, but then now you can do dual catalysis, dual switchable catalysis. One way you can actually control the hydrogenation, as well as you can control the dehydrogenative type of reactions with the same catalyst just by the use of acid and base stimuli in the system. So this kind of system, which has actually control on two reactions, are extremely rare, and we have been fortunate here to design this kind of catalyst in artificial way, and we implemented in different kind of imines. But then one question remains here, what about the activity? Why is the difference going on? So in our group, we do a lot of mechanistic studies to understand the processes so that we can go ahead with a proper understanding. So during the mechanistic studies, mostly we focused on the kinetics. In this case of hydrogenation, we found that the inactive catalyst, the rate is governed by the catalyst concentration, H2 concentration, as well as the imine concentration, whereas in the active catalyst, it is governed by catalyst concentration, H2 concentration. So what is going on here, to cut long story short, what we found, the Kh by Kd, for the inactive catalyst is also showing some effect. It's more than 1. So that means that is involved. But in case of 2, it is, for H2 and D2 comparison, it is much more. So what is going on here? In case of active catalyst, let us see first. Once you remove the iodo here by your solvent and take the H2, then the bifunctional activation of the H2 molecule is very much effective here, and you are making the hydride. You see that you are making the hydride here very effectively, and the proton is captured by this basic moiety, as I explained earlier. Now, once you have the hydride, that can actually transfer the hydride to the imine very effectively and get the amido, which is again released by the slow step of hydrogen interference, and that is what the rate determining step is. You are releasing the amine, and then you are regenerating the hydride, because this is acting as a kind of basic ligand to clip the H2 again. So this is what the chemistry behind the active catalyst, where the hydride, iridium hydride, is the the key factor, generation of the iridium hydride. Whereas in the inactive catalyst, because you don't have such basic moiety to clip the H2, you see, the H2 is coordinated as eta 2 mode, kind of H2 molecule as such. This is also known in literature. It's not something new that we are proposing. There are H2 coordinated molecule also. Unfortunately, it cannot be clipped in our catalyst, and it has to go via, this is our proposal, kind of outer sphere transfer to your imine, and that is not very much effective. So basically, we are stuck at the H2 coordinated molecule, and the hydride proton transfer from this type of system is not so easy. That's why this catalyst is either inactive or very much low active. So how do we know that this active catalyst is forming hydride and this is forming H2 coordinated metal center? We did a very classic signature test that is called variable temperature spin lattice relaxation time analysis. What we do actually, we measure the spin lattice relaxation time T1, but that you have to measure minimum. So when you have a coordinated H2, that can actually relax very fast, because this bond is not so strong and this time would be very low. So you see here, we measure the T1 minimum, and this is 49 milliseconds. That means extremely fast. In case of active catalyst 2, where I propose hydride, there it is, T1 minimum is 390 milliseconds, almost 400 milliseconds. Now from literature also you can see anything below 100 millisecond T1 minimum is going to give a clue that it is a kind of iridium H2 coordinated molecule, whereas anything beyond that, as much as possible, let's say 400 even up to 1000 millisecond also, these are indicative of iridium hydride. So we have actually analyzed and we have proved that in the active catalyst we are in fact generating hydride, whereas the inactive catalyst case we are not generating the hydride as per our proposal and as per our experiments that we have in our hand. What happens to the dehydrogenation? Why the imino is now active, why the amido is not active? What is going on here? Here the rate is more or less similar in both the case, amine concentration affects. But what happens, because this amido is electron rich ruthenium, now this is too much electron rich because of this amido coordination, as I can prove by electrochemistry that this is more electron rich. Now the amine coordination, because for dehydrogenation your amine has to coordinate fast. Amine coordination is little bit problematic here, and you see the equilibrium constant for amine coordination for this compound, the amido one, is really low, whereas the amino is very fast. So that means the strong binding of amine followed by dehydrogenation plays the key role here. So that means the electronics is governing here for your amine coordination, which is very good in case of the immunocatalyst, which is active now in dehydrogenation, which was inactive in case of hydrogenation. So that's the acceptable mechanism and proposal that we have put forward. Of course, a lot of computational studies we have been doing to understand in depth, but of course it will take a lot of time. So what we have developed till now is this chemistry. So this is what the development of the chemistry has been done over a period of 2-3 years, that we realize the chemistry, how it is getting controlled, this hydrogenation and dehydrogenation. So the basic condition is very good for hydrogenation, acid condition is very good in dehydrogenation, and we are actually switching back and forth these catalysts between active and inactive, between imino, amido and imino, and so on and so forth. But those are aliphatic C11N group. But in the LOHC, I never showed you. I showed you aromatic C11N. So what about that one? That is difficult. Now you have to compromise with the aromaticity. So that means that is difficult reaction as such for the aromatic C11N group to hydrogenate. So how to do that? For that we had to again go to our chemistry and we had to modulate the catalyst. In this case, we are actually incorporating a different kind of acid-base switchable moiety, which is an amide based. It's an uracil derivative which we are using, and the abnormal NH we are still keeping. That is our key for our catalyst design. But this case, it is very important here, because in this, if you look at this amide, then it can actually participate in resonance like this. This part can be kind of resonance or tautomer. It can come here, and this O minus can go there. So basically it's an amidato kind of resonance is possible, and that is very key for us, because what happens in this O minus, once you have the other resonating form, that can cleave H2 in a bifunctional manner that I was discussing earlier. So basically this O minus will take up the proton and the metal will take up the hydrogen, right? So this is what the bifunctional type of mechanism that I was discussing, which is perfectly fine with this uracil backbone as well. Now this OH is a proton source, and that is our key for the aromatic C11 hydrogenation. These are difficult, but then what we have to do here, we have to activate this by protonating the C11N particular group. So if you protonate this imine, then it becomes more electrophilic, then the hydride transfer easier. But then how can you protonate? Because in the previous designs, what we had done, all the hydrogenation was active under basic condition, but then under basic condition you cannot protonate. So that's what we have designed here, that I should have a kind of acidic conditions now, or if not acidic, I should have proton for the hydrogen. So it's a kind of reverse concept. So for doing the reverse concept, we have introduced this design so that this proton will be utilized by this particular aromatic C11N group, and now the hydride can be transferred. So for consecutive proton and hydride transfer, once you generate this one, so the proton transfer will go first to this the aromatic C11N, followed by hydride transfer, so that you can get the loaded compound. And in fact, it is active under this condition. Now, how do we know that it will not act as a basic in basic condition? Now you put base, what happens? The base can take up the proton and then it shuts down the proton transfer. So under basic condition, you cannot do this reaction. This is switched off. But under acidic condition or neutral condition where you have this proton, this reaction is switched on. So this is what the design principle behind this for aromatic molecules that we have incorporated here. This is a very clever design to activate. Otherwise, very difficult to activate this aromatic compound. Okay. So in fact, we have tested. You see, these red lines are with base, no active or very slow, or the blue lines you see, these are under acid or under neutral condition that are active here, either this one or that one, and you can also switch back and forth, active, inactive, active, inactive, by the addition of acid and base in a consecutive manner. And then we have actually tested a lot of LOHC molecules based on this platform. There are H here, there are methyl substituted here, and so on and so forth. You see the proton transfer first, followed by hydride transfer, and then consecutively into the other bond also you can get this loaded compound. What about the dehydrogenation? We tested the dehydrogenation, that is a back reaction, the loaded compound to the unloaded compound, and it is also perfectly fine in our hands with the current catalyst that we have. We have quite a bit promising results in case of dehydrogenation also. We could achieve very high yield under good conditions, good ambient condition I should say. Although now we are working to reduce the temperature as well for the dehydrogenation reaction. In all these reactions, our hydrogenation H2 loading step, we never used any pressure. We have done at atmospheric pressure in all the catalysts, including the aromatic case also, which was never achieved in the literature so far. What about the other LOHC that has been proposed earlier? Let's go into the formic acid. What about the formic acid? So formic acid and formate are kind of acidic and basic version of the formic acid, right? You can actually, depending on the pH, you can have formic acid or formate. But then how can you bring in the formate of formic acid? By H2 hydrogenation of the CO2. So what is our strategy is that we will trap the CO2 with base to form the bicarbonate. Depending on the pH, you can form carbonate also, and the pH, if you now go to a little bit of acidic, then you can get bicarbonate. So this is a trapping step, and then followed by this trapping, now you load H2 to get your formate. Formate can be again change the pH to get your formic acid, which can be again unloaded to get your bicarbonate back, and that is the way you are actually completing the cycle. So this is our target in case of formic acid things. Now again for carbon dioxide also, as I mentioned, our target is to achieve this reaction at atmospheric pressure with quite a bit good turnover frequency. So that is our target. For that one also, we have actually modified the catalyst here. We have changed this one to this abnormal NHC. Now these are very long story. If you ask me how did you do that, this is a very long story. So not for this talk, in the paper or maybe in a personal discussion we can discuss. So what we have done here with this iridium catalyst, you look at the hydrogenation of CO2. We have very good results here, at least achieving to almost 60 hour inverse turnover frequency at normally ambient condition, which is a good record for this kind of reactions in case of CO2 to formate or formic acid. Discharging also we get a good result here. So for this catalyst are concerned, this discharge means the dehydrogenation is a highly pH dependent. I will show you later. At pH 4.4 we get the highest turnover frequency, we get the H2 back and CO2 back, and that CO2 can be recycled again by this scheme. So we could achieve this formic acid format also. How do we monitor? As I told you, the typical hydrogenation run we monitor, you see, by looking at the generation of the iridium hydride in the negative region at minus 14.8 for our typical iridium hydride catalyst or the complex. This is our signature hydride peak in the negative region, and of course we monitor the generation of the formate here in the proton NMR at 8.4 or 8.5, 8.46 ppm in the proton NMR. Similarly, the dehydrogenation step also you monitor. We can see the H2 generation by simple proton NMR. You can look at H2 dissolves in your solvent, and it can actually pop up in your 4.54 region in the proton NMR. And how CO2 we are trapping? CO2 we are trapping in base, and then we are monitoring the carbonate formation by looking at the 13 CNMR at 169 ppm. So that means I'm generating H2 and CO2 back in my dehydrogenation reaction, in my release reaction. So that we have monitored. Now how this reaction occurs, again the mechanistic rationale is like that. You look at the carbon dioxide plus water when we are trapping, then depending on the pK of the solution, either it will actually exist as bicarbonate, or if it is a little bit stronger base, then it can also act as carbonate. It can exist as carbonate. Now what happens, the more and more CO2 you dissolve in the solution, then the pH becomes little balanced at around pH 8.5 that we found in our solution. So in pH 8.5, most of the carbon dioxide liquid, I mean dissolved carbon dioxide, are bicarbonate, not carbonate. Carbonate is actually more than 10. If you have around 11 to 12, then you will get carbonate, and the rest of course gaseous CO2 that you have. So what you have in the beginning with your iridium catalyst, once you have the H2 molecule coordinated, it can actually give you hydride by bifunctional mechanism that I told you, and then the hydride can be delivered to your either CO2 gas or bicarbonate to form your formato ligand, and then that can be released again to regenerate the catalyst and go on. And the dehydrogenation case also, you just look at, as I told you, the pH 4.4, it works best because the pK of formic acid is 3.75 to generate the formate. So at 4.454, around all the formic acid exists as formate, which acts as a very good ligand at the iridium center, followed by a beta hydride elimination. You release the CO2, you make the hydride, and then hydride will be protonated in the medium to get your hydrogen back. So basically in pH 4.5, you have the proton, so you are getting the hydrogen and CO2 back. As I told you, we have monitored both the cases. Now, so what happens, we are using H2. So in the case of CO2, what happens, we decided that, okay, H2 molecule, as I showed, unless and until, I mean, maybe in near future, we will find out a better H2 generation procedure with renewable energy. We do not have at this moment. We are generating H2 at this moment currently in the world from fossil fuel. That is steam reforming, all of us we know, but that is again carbon emitting strategy. So that is not very much green procedure or carbon neutral procedure. Once we have the water electrolysis technology which is viable, we will have the renewable H2. But then what we thought, that why not use the nature's currency? Nature has already made this reduced biomass, which actually can be used as such for this reduction of CO2. So what we decided, that we use the nature's alcohol as the hydride source. Forget about the H2, because nature has already fixed the H2, not as a H2, as a proton and hydride, proton and electron, as you can say, to be precise. So already the hydride is there in nature's compounds, for example, glycerol, which is a byproduct in biodiesel production. It's a cheap product. We used glycerol as the hydride source, not H2, and we used ambient pressure of CO2, and we could achieve formate production in a very high turnover frequency as per the current literature status is concerned. For example, 150 hour inverse at atmospheric pressure. So this is a quite amazing result to us, and we have been now working actively in this area, that how we can actually increase this one and make it more practical with nature's currency to reduce the CO2 or to hydrogenate the CO2 or to reduce CO2 to its reduced product format or even further. So this is a quite amazing result, and this chemistry world they have actually highlighted, because this is very important result in case of you are using nature's currency to again recycle CO2. As you see here also, you can monitor with respect to time. This is the formate formation, and with respect to time also, the rate is not going to diminish as long as you feed CO2. The rate is constantly increasing. So it depends on the feed of CO2. Mechanism is very similar here, depending on the CO2 medium that you have in the reaction medium. CO2 can be can exist as bicarbonate or carbonate. Of course, here also we show that either bicarbonate or CO2, not the carbonate. And same way you generate the hydride from the alcohol. So basically I have the base and alcohol. We use probably KOH in this and K2CO3. So this glycerol and base form the alkoxy, from where you generate the hydride, which is transferred to your CO2 or the bicarbonate. So that means we can use a non-H2 source also to reduce the CO2. So if we combine these two CO2 proposal, CO2 formate proposal, then either you use H2, of course, this is a big question. So I need H2 as a renewable to make it viable. So this is what I need now. But for the time being, we are using non-H2 source, nature generated non-H2 source like biomass, to reduce the CO2 which is in fact it is trapped CO2. So I have captured CO2. In fact, we demonstrated this with nature, normal air. So we have bubbled air. We trapped the CO2, whatever concentration that you have in air, as a bicarbonate, and then we actually implemented that solution into our hydrogenation. We generate format, and then of course, as I told you, the format under a pH 4.4, basically it's a formic acid, I can get my H2 back. So this is what the summary of this particular formic acid CO2H2 LOHC component. And if we summarize whole work, then of course this is what the catalyst which is active at this moment for this reaction, and for the other liquid LOHC compounds from C double bond N kind of bonds, we have several catalyst design, and we are still going up with further design. Currently, we are working to replace this noble metal, but that is not going to be easy, as I told you. Everybody is trying here, but no success so far. Some discrete examples are there with iron, manganese, and all other. But of course, based on our understanding and knowledge that we have gained, we are now going towards cobalt and iron to achieve these very important hydrogenation dehydrogenation reactions. And hopefully in future, I will be talking about that as well. Finally, I would like to acknowledge the funding agencies. ISAR Bhopal, they have been very generous to give a lot of funds in our new institute to all of us, and including me also. Then ACRB, they have been also generous to give me a lot of funds in terms of different scheme projects. Then DST fast track when I joined, BRNS fast track when I joined. And of course, the main pillars of all this research, as usual, are the students. You see here, they look very energetic in this, chemistry, all of them. I do different chemistry, but of course, the group is looking large. So I am very much thankful. They motivate me a lot for doing this kind of difficult chemistry, I should say. But of course, they are the main pillars of all this success. And specifically, I told today work from Srivats. He already he completed PhD. Abhishek is continuing integrated PhD in my group, and Babular. So these three are the main heroes of today's work that I have presented. So finally, thank you very much for your kind patience. And of course, I would be very happy to answer any question. I don't know how much more time I have, but again, thank you very much for giving me the opportunity, and I would be really happy to answer any question that you have. Thank you.
So, thank you, Professor Choudhury. And as we are running short of time, I invite only one or two questions, small questions, so that I can answer.
There is a question in the chat box from Dr. Joydeep Gangopadhyay, that is, in the inactive form of ruthenium catalyst, metal coordinated hydrogen forms a 4-member ring with the imine followed by elimination of reduced amine. What is the stereo configuration of the 4-member ring, planar or puckered? How could we conclude that sigma electrons of hydrogen are donated to high energy pi star of imine in the final reduction state? Is there any NBO analysis?
Yeah, so that's true actually. So this is really high energy, as you mentioned. This is extremely complicated situation here. We do not have here computational support. So only support that we have at this moment is the coordinated H2. So what happens here also, the probable thing would be little bit of polarization of the coordinated H2 molecule. The moment you have the polarization, then you can have similar kind of hydride proton transfer. It's not that the sigma electron is going, it has to polarize. So it's not like oxidative addition mechanism that you are actually dumping into your sigma star. So it's not like that, or you are giving away your sigma bond. So it has to be kind of polarization mechanism here as well. But of course, it's not that much polarized like your hydride and proton, separated hydride and proton. So whatever polarization, but normally we know that when H2 coordinate, we do polarize this molecule and whatever. So that's why the computational support probably would help us in future. So this is a little bit gray area, if I'm really honest to you. But what we believe that definitely polarization is going on, and then the proton hydride transfer would be very similar, and that's why the rate is extremely low here or almost inactive, but the mechanism would be very similar to the hydride proton transfer in a concerted way. See, there are some intramolecular proton hydride transfer where the hydride and the proton are very close to each other to your substrate. That time also this kind of outer sphere, these are called outer sphere hydride proton transfer occurs. There are mechanistic support and lot of studies are there with that Joyanta catalyst, and there are so many where you have the hydride, metal hydride, and the proton from the ligand side, basic side. So they are close to each other and they form the transition state, cyclic transition state with the C double bond O or C double bond N that you have. So that outer sphere hydride proton transfer is known, concerted. So we believe that it can be very similar to that, but of course we are not 100% sure that that is the only way here. We will look into this matter, but that is what the probable explanation at this moment that we have based on current understanding and the data that we have.
Sir, okay, one more question only we will go in this session. So what kind of, this is from Dr. Subhashish Bishwas.
Yeah.
What kind of computational study you are doing on metal hydrogen regarding catalysis, DFT or HF-DFT, and what are the basis of choosing these studies?
At this moment, we are not, computational experts. So whatever we have learned from our previous experience and my own PhD postdoc research, we are not computational expert. We do take help from computational friends and colleagues. But normally we do DFT with the accepted basis sets with proper solvent correction and dispersion corrections with the D3 parameters. So we do, because these are highly entropy dependent processes, so we have to take the solvent and the dispersion corrections into our account. So we do DFT with those corrections incorporated, and we do normal DFT actually. We do not do any other studies, parallel studies in these cases. We do study the reaction energy and the barriers for all steps, and that is how we are trying to achieve at this moment, and specifically the hydride, metal hydride generation followed by its delivery. So that is what we call it hydricity. So those things we study at this moment in our group, but of course we are trying to collaborate with other expert computational chemists to help us in this regard.
Thank you very much, Dr. Choudhury. Now I'll hand over the session to Dr. Bastia.
So, thank you again, Professor Choudhury. Definitely I can speak that you are a prolific speaker.
Thank you very much.
Very good speaker, and the topic you have chosen towards that, I know, that hydrogen economy and switchable catalysis. These two are definitely two new words, two new fields. So definitely your talk will help our new researchers to a great extent. So on behalf of our organizers, I once again thank you. Thank you, Professor Choudhury.
Thank you very much. Thank you very much.